Hello and welcome. Today we're going to be deriving the heat equation. So finally we're going to get to actually developing a PDE that's solved. We're going to actually do a PDE describing a real physical system. So the idea here is we have a rod. And the rod, you can think of it like that. And it has a certain fixed cross-sectional area. So A is that cross-section. A cross-sectional area. And for this video, that's going to be fixed. Okay, it's going to be a constant. So in your homework, in problem 1.4, the cross-sectional area could change. It could be non-constant. Okay, and you'll be asked to derive the similar PDE in this case of a non-constant area. But for the video that we're going to show here today, we're going to be talking about a fixed area. Okay. I'm going to change my colors here a little bit. Let's go with a little bit brighter color. I like that. Okay. Now what I want to do now is we're going to start with a few things. We have to start with a few physical constants, right? So first off, let's talk about how do we measure heat in a metal rod. So heat, heat of course is the transfer of energy, and it's thermal energy we're talking about. Okay, so thermal energy, of course, is energy that's not from chemical bonds per se. It's not from melting or phase changes or anything like that. It's typically the thing what we talk about is actually what we call sensible heat. So sensible heat means exactly that. It's the idea of touch. If I were to touch a hot object, you would sense energy entering the finger. Okay, so that's what we mean by sensible heat. There are other types of heat transfer. Of course, there's radiation. We're not going to be talking about that. We're going to talk about basically the actual heat transferring within the rod itself. Okay, so not into the outside world. All right, so this is our framework. Let's go to the next page. What we have here is we're going to write our rod again, and it has that cross-sectional area. Now let's define a few physical constants. Okay, so let's define h of x comma t. This is going to be the energy density in the rod. Okay. There's also going to be u of x comma t, and that's going to be the temperature in the rod. Okay, and remember our spatial domain is going to be horizontal here. Okay, and of course we have A, that cross-sectional area. So how we start this, the other thing we want to define is another thing, which is UAB. And this is going to be the thermal energy in an interval. Okay, so h of t h of x comma t, that is going to be joules per meter squared, right? Or meter cubed, sorry, per volume, right? Joules per meter cubed. Okay, and this is going to be in Kelvin. So we'll call it K, okay? So J per m cubed, okay? And this, of course, is going to be meter squared, right? And this big capital U variable, that's just going to be the integral from A to B of our energy density, like that. But we're going to do one more thing. We're going to multiply by that cross-sectional area. So this will have units of just joules. Okay? So, of course, joules is really important because this is conserved. So energy is conserved. Energy is a conserved variable. So what happens is, of course, is the conservation principle applies. Okay, cool. All right. What we do, of course, the conservation principle says d capital U dt. So the conservation principle, that means that du dt has to equal what? It has to equal the negative flux at boundaries plus sources. Okay, so we can write that as the flux at A minus the flux at B plus the integral A to B of any source of x comma t dx. But what we're going to do is multiply everything by that cross-sectional area. And by doing that, what we're going to do this now is we're going to define phi is going to be joules per meter cubed, all right? So J over m squared, meter squared. So that's going to be the, we also have to have seconds down there, okay? Because it's always going to be per unit time, right? Per second, okay? All right, so of course, then that means that A times phi is going to be joules per second. Okay, good. All right, we want to have that. And that makes the units work out because, of course, the units of du dt is going to be joules over seconds, right? Right, same thing with R. That's going to be a source per meter cubed, right? All right, so that means, of course, that R times A times dx, that's going to be, of course, and by a source, of course, we mean joules per second. All right, so that's how much is being inputted in it. So that's going to be, of course, joules per second, just the same. So we have the same units for everything now. All right, so now let's go to the next page. Let's draw out what we had before. Du dt is equal to phi of A minus phi of B plus the integral A to B of R of x comma t dx. But now we're going to put that A everywhere as well. Okay, so now we have, this is our equation. This is our conservation principle. Okay, it's also known, of course, we can write it this way. This is actually the continuity equation in integral form. That's also what it is. So remember that from chapter 1. So now, of course, we can do a little trick here where we actually say that's actually equal to A, the integral over A to B of the partial derivative of phi per x dx, like that. And of course we have this. But recall that this is d dt, and remember what u is. U, of course, is the integral a to b of h of x comma t times a dx. Okay, So it looks like there's everywhere here, same integral on all terms. Okay, cool. So that means that we can now take the integral outside. I can put it like this, like that. And then on the inside, I'm going to move that inside there. And what we're going to get is the partial derivative in time of the energy density times that A value is equal to negative A partial derivative in space of the flux plus A times R, and we don't need that much space. I'll put the dx there. Right, so this is the equation we have inside, and it's starting to look like a partial differential equation. The problem is that there's no single variable that we're using here. So basically we can relate H to phi, but so what we need to figure out is actually, this is the flux, right? So we got to figure out what the flux rule is. Well, the flux rule, it turns out, comes from a physical principle called Fourier's law. And it states that the flux is going to be equal to negative Kc times the partial derivative of temperature in space. All right. So Kc, that's called the heat conductivity. And it's a material constant. All right, so you could look up, e.g. iron, copper, steel. They all have different parameters for this that have different levels of conductivity. So for copper, in fact, this number is very big. For iron, it's actually smaller. Steel is somewhere in the middle. So of course, you might have heard this, but copper is very popular. It's a very expensive thing to make pots and pans out of, but it's something that chefs really like to use copper to cook in because when you put it over the stove, that pan has a very high heat conductivity. So that's used a lot. But of course, other people really like cast iron for cooking. Although it has a low heat conductivity, it has a very large heat capacity, which is a different concept. We won't go into the details of all that yet, but the idea here is that these metals can have different characteristics, and so they have different physical parameters. Okay. All right, so what we're going to do, though, is we're going to now, of course, we're going to... I'm going to try to get the right color here. So with that parameter there, we can now put this in everywhere we see phi. But the other thing we want to do now is relate H. So this we call the energy density. So that's a difficult thing to measure. Mostly it's hard to measure. It's hard to measure directly. And the energy density is a bit of a misnomer because, of course, there's lots of energy in matter. The energy could come from bonds. It could come from how the molecules are arranged, whether they're in liquid or solid form, the phase of the material. Energy could be stored in kinetic energy. Maybe this rod is hurtling across across space at a very high velocity. All of those are different types of energy. So energy density is a bit weird, but we're talking about, of course, thermal energy. Thermal energy now. So let's see if we can do this one. So thermal energy, we can actually relate this. So it turns out that H of x comma t relates to temperature. by C times rho times U of x comma t. Right? Remember that U variable, that is temperature. Okay. So what we have to now is figure out these two constants here. So C, that's what we call the specific heat. And of course, rho is the common parameter we talk about for mass density. Okay. So we said that H has units of joules per meter cubed, right? All right, and of course C has units of well, let's see if we can figure it out. These have to be equal to each other, right? C times rho times U. Okay, that has units of Kelvin. Okay, and C, that has units of joules per Kelvin per kilogram. Okay, and the mass density has kilograms per meter cubed. Okay, so if you multiply all those together, you get units joules per kilogram per Kelvin kilogram times kilogram meter cubed times Kelvin, and you see clearly the kelvins cancel, the kilograms cancel, and we're left with joules per meter cubed, which is the same thing as on the other side. Okay, cool. All right, so that means what we have here, though, I'm going to go back up there. There's our flux law. Our flux law relates flux to a temperature gradient. And our specific heat parameters relate energy density to temperature. So now we should be able to put these together in our PDE that's sitting up here. So let's bring that down. And now I'm going to do that. So I'm going to write it again. So we have, what we have now is A times the partial derivative in terms of time. But instead of putting H there, I'm going to put C times rho times U. And of course, that's going to equal A, C, rho, partial derivative of U with respect to time. And that's equal to negative A times the partial derivative of space of the flux. But we're going to put in for flux, we're going to, of course, put in our Fourier's heat law. Like so. And then finally, we have A times R, which just sits there and does its thing. That's sort of the catch-all term. So this is our PDE. I'm going to select this now. I'm going to copy it, and now I'm going to move it over to the other page. I'm going to paste it. There we go. Now let's see if we can now just simplify this down a little bit. We have A, C, rho, partial derivative of U with respect to time, is equal to negative A times K, C. Oh, but remember, the negative and the negative cancel right there, right? So this negative here and that negative there, they cancel each other. And we get A times Kc. And then we get a second spatial derivative of temperature. Okay? Plus A times R. Also note that the constants A cancel. Okay, we can divide those out. The next thing we're going to do, finally, is divide the whole thing by C times rho, in which case we're going to get partial derivative of U with respect to time is equal to this parameter we'll call D times the second spatial derivative plus R over C rho, where D is this parameter called the heat diffusivity, and it is equal to Kc over C rho. And again, this is a material parameter. It's something you can look up. You could Google heat diffusivity. You could, it's going to have different numbers for iron, copper, steel, etc., etc. Whatever metal you could think of, and other things that aren't metals at all. A lot of all materials have a heat diffusivity property. Solid materials. Okay. So we might want to let's just stop here. This right here is now what we call the heat equation, partial differential equation, PDE. Okay? And this is what we're going to be studying a lot in Chapter 4, is this heat equation, how it works. But we want to talk about maybe what the units of this are. Okay, so we said the units were the parameter Kc over C rho. Let's just sort out what that is. Let's remind ourselves that the numerator had a parameter of joules per Kelvin meters second. Okay, and specific heat had units equal to, let's see here. Let's see if I can remember what it is. We know it's going to have to be joules per Kelvin per kilogram. Okay, and then this is going to be, and for kilogram it's going to be meters, kilogram per meter cubed. All right. So that's our units there. Now let's get to canceling all these things. We see there's in the two denominators there, the kelvins cancel. The kilograms cancel. One of our meters cancels. The joules cancel. And we're left with meters squared per second. So that is our units of the diffusivity parameter. So this is what I call the essential PDE parameter, because it relates space to time. It basically tells you how far heat spreads per unit time. And it does so in meters squared per second. Okay. So again, a material that has a higher heat diffusivity, heat spreads quicker through the material than a material with a low heat diffusivity. Okay, so that's how we derive this PDE. I'm going to stop this video here. We're going to start now playing around with solutions to these PDEs in short order and discussing all the physics of them, but we finally derived it. But in your homework, let's now just talk about that homework. Remember, we have A goes to A of x, right? The issue we have to deal with here, the real crux of this issue, revolves around this. We have this partial derivative of h with respect to t times a, integral a to b dx. Recall this juncture in the problem, and what we had was the integral, back up there. We had that phi of ax now of aa minus a b phi b. All right, plus a integral a of x r of x comma t a to b dx. Okay, so it's in this stage here that you have to put this into some integral, a to b, right? And what you put there, I think, is what's really going to unlock the issue of how to derive the PDE when you have now variable cross-sectional area. So the kind of situation is where basically our metal rod now might have variable cross-section. So it could have A here, but then it could have a bigger cross-section in one part and another. Of course, when you have a bigger cross-section, there should be less resistance to heat traveling through it, that you should get greater you get greater flux, all things considered. It's going to change the dynamics of the situation a bit. So, but the real crux of this problem is going from this step to this step, and it's figuring out what to put there. So hopefully that fills in and gives you a roadmap for success for solving that problem in Chapter 4. So thank you very much.